Today's lesson is on continuity. We're trying to figure out where the function is continuous and not continuous. The concept of continuous is very simple if you look in terms of graph. So let's pretend that we have a graph of some kind of function. Let's say something like this, some kind of x to the third graph. We could easily tell that this graph of f of x is continuous because it's not interrupted from negative infinity to positive infinity. Now the second example of the graph that I'm going to draw will be not continuous because it will be interrupted somewhere in the middle. So something like, let's say we have this parabola of g of x. And notice that from negative infinity to positive infinity, there's a hole somewhere positive x-axis side. So the easy way to tell if something is continuous looking at a graph is if you're able to draw it from left to right without lifting your pen. But the question is, what happens if you cannot draw the graph or you don't have a graph to look back to? So let's look at the definition of continuity at a point. So in case we have a complicated graph to sketch, a function of f of x is continuous at point C when these three conditions are met. First, f of c has to be defined. Limit as x approaches c for f of x has to exist. And the last one is limit of x approaching c of f of x has to equal to f of c. So as long as these three conditions are met, we could say that it's continuous at that point. And if every single point on the graph is met these conditions, then we could say that the entire graph is continuous from negative infinity to positive infinity. Let's examine example 1. It says determine if the following function is continuous at x equal to 1. Okay, previously we just said that definition has three conditions, so we're just going to go through all three of them. First condition was f of 1 has to exist. So I'm going to start by factoring first, because you want to simplify it all the time. To solve for the value, we could say that f of x in this case is same thing as x equal to our f of x is x plus 1. And there's a hole at x equal to 1. So the fact that there's a hole at x equal to 1, we know that f of 1 is undefined. And again, we could figure that out by substituting it in right away. Right? 1 minus 1, 1 minus 1, you'll find that to be indeterminate form. In other words, it's not defined. So what does that mean? It means that at x equal to 1, this graph of f of x is not continuous. It says determine if the following function is continuous at x equal to 12. So same thing, let's start with f of 12. So it says that x equal to, it says that x is greater than or equal to 12 for this graph. So x equal to 12 must be belonging to this top graph of piecewise function. So 12 plus 13. And it seems like you do have a point, so that means it is defined to be 5. Now, second condition was your limit has to approach 12, and you need to have a limit. So this is a piecewise function, so you probably have to look at left side and the right side of it, since the breakpoint in this case is 12. So let's find out limit as x approaches 12 from the left side, and limit as x approaches from positive side. So negative side means that you're approaching from less than 12 value, so we're using this bottom graph or bottom function, x squared minus 9x minus 31, and this could be solved with direct substitution. 144 108 minus 31 is equal to 5. From the positive side, has to come from the greater than 12, so we're using radical x plus 13, which comes out to be also 5. So left side and the right side both agree, so limit as x approaches 12 will equal to 5. And very last condition was basically the first point and the second point has to be exactly the same. F of 12 is equal to limit as x approaches 12 for f of x, and we were able to see that they're both equal to 5. So what does that mean? It means that f of x is continuous at x equal to 12. There's two types of discontinuous. So if any one of those three conditions failed, we know that it's discontinuous at that point, since it's not continuous. The two types of discontinuous is known as removable and non-removable. You might have heard this term before. We learned that if you have a hole in rational function, we call that a removable point. If you had a vertical asymptote, we call that a non-removable. So easy way to think of these discontinuous is we call it removable discontinuous if you could be replaced with a point. So typically, removable discontinuous will happen when you have a hole. Non-removable discontinuous is something that you cannot replace. That's known as vertical asymptote. Or piecewise function. So if you go back and to look at number one had a hole, so that will make it removable discontinuous at x equal to 1.